Hi, this is Group 30. My name is Xavier, and then this is our second assignment. So, our work is about transfer function. You're supposed to find the factor by which the gain k of the transfer function can be reduced from 60% to 20%. And the transfer function is g of s equals k all over s into bracket 1 plus st.
So our open loop transfer function g of s is giving us k over s into bracket 1 plus s of t. And then we factor t out and then divide our numerator by t. That gives us k over t all over s into bracket s plus 1 over t. And then we have our closed loop transfer function t of s giving us j of s, that's this function, all over 1 plus j of s. And then we substitute what we got here into our closed loop transfer function t of s, and it gives us k over t all over s squared plus 1 over ts plus k on t.
Found we've got our closed loop transfer function t of s. We'll compare it with the standard second order form, and by comparing coefficients we'll have our natural frequency omega n to be square root of k over t, and then our damping ratio equation 2 zeta omega n will be 1 over t. And then in making zeta the subject, we end up getting this expression 1 over 2 square root of kt. And then finding the relationship between zeta and k, because k is in the denominator, we have zeta being inversely proportional to 1 over square root of k.
So calculating for the damping ratios for overshoots, the formula for the overshoot is inertia minus zeta pi all over root of 1 minus zeta squared. By making zeta the subject, we get this expression. So then we are supposed to reduce the overshoot from 60% to 20%. So we set 0.6 here to get approximately 0.16, then 0.2% to gain the final 20% of approximately 0.456.
We are finding the gain reduction factor, and K1 equal to initial gain, K2 is reduced gain. K1 over K2 equal to the square of theta 2 over theta 1. K1 over K2 will give you this squared, and you get 8.12. And then the gain must be reduced by a factor of approximately 8.
Relating our damping ratio to our overshoots, we had zeta to be equal to this, and we had our initial value to be 0.16 and our final value to be 0.456. Now, substituting these values into this, we had k to be 8.12. So the gain must be reduced by a factor of approximately 8 to reduce the overshoots from 60% to